Good morning, everyone. So, we are looking into the macroscopic balances of the various conservation equations, mass, momentum, and energy in a fluid flow problem. And in last class, we have seen lots of quite a bit of examples of conservation of mass and their application, and to determine various quantities in a flow domain. Now, today we will be looking into several examples of momentum balance equation, and how we will be getting various determine various quantities of interest by doing a momentum balance equation. Now, the first problem I will be having, you have a metal container there is one port in the top, there are two ports in the side, and the metal container is resting on a scale, on a balance. Okay. So, your fluid is coming at point 1, port 1, it is going up out at port 2, and it is going out at port 3. Okay. And the height of the container at the steady state is constant, and this height is around 0.57 meter. Okay. So, it is a metal container, its height is 0.57, cross sectional area. Cross sectional area means area of this chamber. Okay. So, area, this cross sectional area multiplied by the height 0.57 will be the amount of volume of water or liquid residing within this tank at the steady state. The cross sectional area of tank or container is 0.09 meter square. Empty weight (2.5 kg), empty weight of the container. Now, area A1 is 0.009 meter square, they are same as A2 and A3. Okay. This velocity, this entrance velocity of the fluid is given, and it is minus 0.15 J meter per second. Your coordinate system is like this. So, it is in the negative y direction. Now, under the steady state condition, this height of the container is maintained at 0.57 centimeter, 0.57 meter, and you have to find out the reading of the scale. Reading on the balance that you have to find out. So, what you have to do? You have to basically determine the reaction force. You have to first of all you have to select a suitable control volume, okay, and determine the reaction force. Do a momentum balance equation in the y direction, okay, and find out the reaction force that will be acting on the control volume in the y direction, okay, Ry. The same by Newton's third law, the same amount of reaction force will be acting on the balance. And once you determine that, balance will be showing that reading. Okay. So, first of all you have to select a control volume. You can select a control volume something like this, just enclosing the chamber, okay, and do an y momentum balance. Okay. Your atmospheric pressure or atmospheric force is acting in all the directions. So, there will be no pressure force, net pressure force acting over it, and you will be having some kind of reaction force, and this determination you just put it arbitrarily in the positive y direction. Okay. Now, the net external force will be Ry minus weight of the empty container and weight of the water content. So, W of tank minus weight of water enclosed into the volume. The volume is basically this height multiplied with the cross sectional area of the tank multiplied by the rho of water, that will be basically indicating the mass of water or weight of the water containing into the container. And of course, you will be having the flow terms on the right hand side of your y momentum equation. If you do so, so F external will be nothing but control surface in the y direction. So V of y rho Vy rho Vy dA. Okay. Rho V dot dA. Rho V dA is basically the amount of differential mass that will be crossing the cross sectional area. So F external will be nothing but Ry minus W tank minus W H2O is equal to this is in the minus y direction, right? Your y was positive here, so you will be having V1 rho V1 A1, right? Now, first of all, this V1 will be minus in the minus direction, so there will be minus sign associated with it, because your coordinate system you have selected is in positive y direction. Second of all, secondly, this V dot dA, the sign of that will be determined by the normal of the area. Okay. Now, V in this direction and a normal in the positive y direction, so that product will be minus. So it will be plus, right? There will be minus sign again coming here, right? So it will be rho V1 square A1, fine. That is M tank multiplied by G minus height times area of the tank times rho of water, that is the mass content of water multiplied by G, that will give you the the weight. Okay. So Ry will be W tank W H2O plus rho V1 square A1. Okay. So basically the effect of water flowing out through the ports 3 and 2 and 3, they will not matter, because you are doing a y momentum balance, they are not coming into picture. Now the reaction force, so this is the force acting on the control volume. So obviously the reaction force on the balance will be minus Ry. So balance, so this will be coming out to be some Newton, okay, in terms of the force, and the balance will show that reading. Okay, mod of Ry Newton. You just plug the values, numbers, and get the values. Okay. Then I have another problem of flow under a sluice gate. And the pressure distribution is given by the hydrostatic pressure. Rho GH. The situation is something like this. You have a sluice gate, you have a gate, okay, you have ground somewhere here, and in the upstream you have water level up to this height, and this distance is, let us say, 1.5 meter. At any cross section in the upstream, the water velocity is uniform and it is given as 2 meter per second, 0.2 meter per second. Okay. Now then water flows out through this, and this distance is d2 and it is 0.0563 meter, and water velocity that is coming out of it is 5.3 33 meter per second. Okay, it's basically water in an open channel flows under a sluice gate. Hydrostatic pressure distributions are assumed at section 1 and section 2. Okay, it is basically rho gh, that will be the pressure distribution. You have to find the magnitude and direction of the force per unit width exerted by the flow on the gate. Okay. So, what you have to do, again you have to, first of all you have to select a control volume. The control volume we select, this is point number 1, this is point number 2, that is the exit point. Through the point number 1 we select a control volume excluding the gate. Okay, and you select the coordinate system, this, and on the gate some kind of reaction force in the x direction, maybe you just assume it is in the positive x direction for the time being, and find out. Okay, so there will be pressure force acting on this, but this pressure force will be function of y, right? And similarly, there will be a pressure force acting on this. This pressure will be acting again on as a function of y, and across this one, there will be atmosphere pressure that will be acting on the gate on both the sides. So it will neutralize. Okay. So the F external you will be getting effectively is summation P1 dA1 pressure in the phase 1 at any y location multiplied by dA1. Okay, that will be in the positive x direction, right, minus P2 on dA2, that will be on the negative x direction. So there will be a negative sign for that, and atmospheric pressure will be acting over the rest portion of phase 2 over the distance d1 minus d2, means over this distance, correct. So in fact, the choice of control volume is basically just edging the this pressure should not be there. It is just excluding the solid object, or you can include it, does not matter. Okay, you can select the control volume something like this. This is phase number 1, this is phase number 2. Water is coming out at that edge, let us say with this distance d2. So there will be pressure force acting on this, that is P2A2, pressure on this P1 A1, and on this area A1 minus A2 there will be atmospheric pressure acting on it, right. It is open to atmosphere, the sluice gate, the right hand side, it is open to here, this portion is open to atmosphere. Right.
This side also will have atmospheric pressure.
This side?
Yes,
no, right, but that pressure will be varying with D2 because of hydrostatic pressure.
So we will have two components, one atmospheric and the other will be hydrostatic pressure.
Right.
So hydrostatic pressure will be varying with
y direction,
but atmospheric
pressure will be acting same in the same way. That's correct. So minus P atmosphere. No, in fact, you won't be having two components of pressure. Pressure at any point will be acting in all directions in the same way.
Then not two components, but means from two things we
are. At this point, it will be hydrostatic pressure only. At the exit point. At the exit point, it is hydrostatic pressure, because whatever the pressure that you will be getting, that will be including atmospheric pressure. We will see the derivation, then we will be getting it. I think there will be some kind of pressure distribution at at this point there will be some kind of pressure distribution at the entry point, but between these 2 points there will be simply atmospheric pressure. Okay. That will be net external pressure plus Rx, the the force, reaction force in the x direction. Now let us look into the pressure at any point of y location. dP dy is given by minus of rho g, and you can integrate this out to get a distribution of pressure y to d, and this will be P to P atmosphere. Okay. So P atmosphere minus P should be equal to minus rho g d minus y, and P at any point will be P atmosphere plus rho g d minus y. Okay, and that pressure will be acting in all directions, so it includes P atmospheric there. Okay, so for phase 1, P1 will be P atmosphere plus rho g d1 minus y. Okay, and for phase 2 we will be having P2 equal to P atmosphere plus rho g d2 minus y. Okay. Now the external force in the x direction will be 0 to d1 P atmosphere plus rho g d1 minus y, w times dy, w is the width in the normal direction, minus 0 to d2 P atmosphere plus rho g d2 minus y, w dy minus P atmosphere w d2 minus d1, that will be the force in terms of force plus Rx. Okay, and this should be equal to the integral over cross section v rho v dot dA. Okay, so at the entry point it will be minus rho v square a1, and the exit point it will be plus rho v v2 square a2. Okay, minus rho v1 square a1, a1 is nothing but d1w plus rho v2 square d2w. Okay, so you carry out these integrations, and w will be cancelled out everywhere, and in Rx it will be Rx by w, so per unit width you will be getting. So the final expression after integration you will be getting as Rx plus rho g w by 2 d1 square minus d2 square equal to rho w v2 square d2 minus v1 square d1. Okay, and Rx by w will be giving you the expression of that. So rho v2 square d2 minus v1 square d1 minus rho gw by 2 d1 square minus d2 square. Now put the values, it will come out to be minus 9.47 kilonewton per meter. Okay, so basically the reaction force that is acting on the gate, force on the gate is basically 9.47 kilonewton per meter minus of this reaction force, and it will be in the positive x direction. Okay, it is these having a flat plus sign, so it is in the positive x direction. Okay. Now again these two problems are from the example problems of your Fox and McDonald. Now I will come to several exercise problems. Problem 4.45. in that book. So you have a tank resting on a car. There is a small car, there is a wall here, and it is tied with a rope or wire with the wall, and over it you put a tank. Okay. At the end, at the bottom of the tank, there is a small orifice or small nozzle through which water is issuing out. Okay. So, water will be issuing out with the velocity v, and you are replenishing the water that is coming out by putting water vertically into the tank, so that to maintain this height h. Okay. So, the nozzle diameter, this nozzle area is given as 600 millimeter square, and this velocity is 10 meter per second. Water level is maintained constant by adding water through a vertical pipe. You have to find the tension in the wire so that the cart is stationary. Now again you have to select a proper control volume and do a macroscopic force balance or momentum balance in the x direction with a reaction force Rx acting externally on the control volume. That reaction force should be equal to the tension, so that the cart will be remain stationary. Just across that volume of water you put the control volume, and there will be some kind of external force acting on it, and water is issuing out with a velocity v2 through the cross section a2. There is no other flow in this problem. So, Fx is equal to this control surface v rho v dot dA. Okay. V is nothing but v2 rho v dot dA is in the same direction. So, you will be having v2 a2. Okay. So, you will be having rho v2 square a2. If you put the numbers, it will come out to be 60 Newton. So, the tension should be 60 Newton in the wire in the opposite direction, so that you will be the cart will be stationary. Okay. The next problem, again an exercise problem 4.46, a slight modification of this. You have a wall, again you are having a cart, there is a vane over it. Okay. This vane angle is 50 degree with horizontal. That means if you draw a tangent here, this will make an angle 50 degree with the horizontal, and you will be having a nozzle here with area AJ. AJ is the area of the jet or the nozzle by which a velocity of with a velocity v, water is issuing out, landing on this vane, then it will be going out, and you will be having a weight kept here through a pulley system of mass m, and you have to find out what will be this mass m, so that the cart is stationary. Okay. And the assumption is the issuing water out of this nozzle with AJ maintains its area of cross sectional AJ when it moves along the vane. Okay. Now again it is very simple problem. You just enclose a control volume across the vane and find out the net external force acting on this control volume. That force should be equal to the tension in the wire, and that tension must be equal to the weight of this body, so that the cart will remain stationary. Then you have to find the mass. Only thing is that you have to do since it is connected to tension, that tension should be equal to reaction force in the x direction on the control volume. So there will be, instead of V, because V is in the positive x direction, this is x, this is y, and you will be having a component of V in the x direction in terms of V cos 50. Okay. You can okay, so V is equal to 15 meter per second in the problem. Area of jet is 0.05 meter square and vane angle is 50 degree. Okay. So this is quite simple problem. So along the vane, this is a vane, and you draw a control volume, something like this maybe. Okay. So since it is open to atmosphere, pressure is acting in all directions, so there is no pressure force, and you will be having Fx is equal to, this is basically Fx or Rx, whatever, this is the external force, that should be equal to cross section V rho V dA. So at the inlet there is no problem, it will be rho V1 square A1 is nothing but AJ, and at the other end you will be taking the component of velocity in the x direction, and this rho V dA will be basically the amount of mass that is going out, mass per unit time, and you will be taking the component of this velocity in the x direction, right. So it will be V cos 50 and since velocity and area in the same direction, now this velocity and area in the same direction, so they will be having positive sign into rho let us say this is V2 A2. Now it is given in the problem that A1 is equal to A2 is equal to AJ. Okay. Since A1 is equal to A2, V1 has to be equal to V2 to maintain the mass balance. Okay. So your Fx will be minus rho V1 square AJ plus rho V1 square cos 50 AJ. Okay. So if you put the numbers, it will come out to be minus 4.02 kilonewton. So the tension in the wire will be 4.02 kilonewton. That should be equal to weight of this body that is hanging to maintain it in stationary condition, and take G is equal to 9.8 or 10. If you take 10, you will be getting mass equal to 402 gram. You know, in the answer of Fox and McDonald, there will be slight mismatch of this number. If you put 9.8, you will be getting around 410, something like that. So that was the answer. If you take 9.8 instead of 10, if you take 10, it will be coming out to 402 gram. Okay. So whenever you will be solving some problems by yourself, you can see there will be slight mismatch of the numbers. So it's basically due to the effect of 9.8 and 10 of G, or if there is some atmospheric pressure appearing in your the equation, either you can 101 kilopascal, okay, or you can take 100 kilopascal, exact is 101.32, something like that. So it's because of this there will be slight mismatch of the numbers. Now second one is also a practical problem, that is an exercise problem 4.48. You will be having an orifice. A vertical plate has a sharp edged orifice at the center. This is a vertical plate with a hole at the center. Now water in this diameter is d, this diameter is small d. Okay, water comes in with a velocity v, it goes out in the vertical direction along the plates, as well as it goes down along the, it comes out of this small hole with a jet diameter d and velocity v, same velocity v. Now we have to find the force required. To hold the plate in place. Okay. This V is 5 meter per second, capital D is 100 millimeter and small d is 25 millimeter. Okay. And okay, fine. Now you have to again you have to select a proper control volume. The control volume you can select this one. Okay. Now this is y direction, this is x direction. So there will be a reaction force, let's say, acting on it. So net external force will be V rho V dot dA. Okay, that is easy to find out. It is positive at the, it's negative at the entrance and positive at the exit in the x direction. Now there will be pressure forces acting on control volume. Okay, what is this pressure force? First of all, the pressure will be atmospheric pressure everywhere. Here it will be atmospheric pressure there, so there will be no effect of atmospheric pressure here. Okay. Similarly, on these portions there is no effect of atmospheric pressure. Now atmospheric pressure is acting on this face of area A1, atmospheric pressure is acting on this face on A2, and the rest portion again it's atmospheric pressure. So it does not matter. So atmospheric, so effect of external pressure does not matter. So another choice of control volume will be, you can enclose the whole thing like a box. Either this can be a control volume or the whole thing can be a control volume. It absolutely does not matter in this problem. Okay. So if you take the whole as a control volume, the total pressure force is on this face is over the area A1. Total pressure on this side will be atmospheric pressure over the area A2, and A2 is equal to A1. So it does not matter. So net pressure force is neutralized. It's acting on the control volume, but it is its effect in the it is basically neutralized. So it's simply Fx is minus rho V1 square A1 plus rho V2 square A2. Okay, and V1 is equal to V2 is equal to V in this problem, and A1 is pi by 4 d1 square, A2 is pi by 4 capital D square. Okay, this is basically circular pipe, it's a pipe. So if you put the values, it will come out to be, the final expression will be rho V square pi by 4 d square minus d square, and it will come out to be minus 184 Newton. Okay, then you have the external force that you have to apply on the plate, orifice plate. Is basically 184 Newton to the right, because it is positive, so you have to apply it to the right. Okay. Then I am having another problem where the pressure forces are not neutralized. Okay, like water is issuing out steadily from a fire hose and a nozzle. Okay, you have a fire hose, and through the water is issuing out through this nozzle. This diameter is capital D and this nozzle diameter is small d. Okay, and steady state flow rate of water is 53. This problem number 4.51. Okay, 53 meter cube per hour, so it comes out to be 0.0147 meter cube per second. Okay, right. Pressure immediately upstream of the nozzle. This is the nozzle. The whole assembly is the nozzle. Upstream of the nozzle means somewhere here. Let's say this is phase number 1, this is phase number 2. Pressure at 1 is 522 kilopascal, and that is absolute. It is not gauge pressure, it is 522 kilopascal absolute pressure. Now you have to find the force transmitted by coupling between the nozzle and pipe. Actually, this cannot be a monoblock construction. Okay, this nozzle must be coupled with this pipe by some external mechanical attachment, maybe bolts or something. So you have to basically find out the external force acting on these bolts or the connection. So you select a control volume. Let us have something like this. So this is the nozzle, the explored version, and we select the control volume, keeping phase number 1, including phase number 1 and phase number 2, and some kind of reaction force, let us say, acting on it. Your Q is given, so you can find out V2. V2 is equal to Q by A2, and this diameter is known, so it turns out to be 29.94 meter per second. You can, since it is a steady state, this volumetric flow rate is constant because rho is constant, and V1 will be Q by A1, and it's turned out to be 7.5 meter per second. Okay, then let us write down the x momentum balance. Rx is the reaction force in the x direction. This pressure is known, it is given, that is 522 kilopascal absolute pressure. So P1 A1, okay, minus PA A1 this is open to atmosphere, so you will be having PaA2, this is PaA2, and over this control volume, just look into the control volume separately. This area is A2, this whole area is A1, the leftover area is A1 minus A2. Pressure is acting with a pressure that is given, that is P1 uniformly throughout this whole area. So force will be P1 times A1 in the positive x direction. On this small area A2, you will be having atmospheric pressure, so it will be P atmospheric times A2, and it will be P atmospheric everywhere in the portion A2, A1 minus A2. So over the whole face on the exit plane, it will be P atmosphere times A1. Are you getting my point? You can look into both the ways. Either you can do total force acting on this area A2, total force acting on the rest area. What is that? P atmosphere into A2 plus P atmosphere times A1 minus A2. So P atmosphere times A2, that term will be cancelled out. So it will be P atmosphere times A1. Or since pressure is P atmosphere everywhere in this cross section, you can say that over this control volume it is P atmosphere times A1. Okay. So whatever way you look at it. So it will be minus rho V1 square A1 plus rho V1 square A2. Okay. Now we just it becomes basically this P1 A2 will be cancelled out, and if you take P atmosphere around 10 to the power 5 Pascal, you can calculate Rx, and Rx will turn out to be minus 497 Newton. So the reaction force will be plus 497 on the coupling. Okay. Then I have an interesting problem on elbow.
Say if we took the nozzle as a control volume, then sir, the area through which the pressure, atmospheric pressure is acting, that will get reduced.
Which one?
If I take the nozzle only as the control volume, rather than taking a box like a control volume.
Let us see. Only nozzle. Okay. That is problem number 4.53. That is a good problem. Water flows through 180 degree elbow. Flow through 180 degree elbow. Okay, it's a 180 degree elbow, and these phase 1, there will be nozzle at phase 2 where water is issuing out, and at the steady state your V1 is given as 3.05 meter per second, your A1 is given as 2600 millimeter square, A2 is 650 millimeter square. Okay, and gauge pressure at point number 1, that is here, is given as 96 kilopascal. Okay, and pressure at point 2, it is open to atmosphere, so it is atmosphere pressure. Okay, now we have to find the horizontal force required to hold the elbow in place. Now, because of the flow, there will be some force acting on the elbow, and so the elbow will move. So you have to determine that force which will be acting on this elbow to keep it in place. Okay. So enclosing the full this thing, you can draw a control volume. So you can draw two types of control volume, either a square shaped something like this enclosing this full elbow, or you can take a control volume something like this. It absolutely does not matter, because over this section atmospheric pressure is acting, over this section the atmospheric pressure is acting. So at these two portions there is no contribution of atmospheric pressure. You will be getting some contribution because this pressure is not atmosphere, it is given something 96 kilopascal gauge pressure. So either you take that, or you take the full square of control volume including the whole thing. Okay. So P1A1 is the pressure force acting on it. On this part, it is P atmosphere times A1, the pressure force acting on it. In this portion, this same area is there, P atmosphere on both sides neutralize. In this portion, same area is there. Okay, they will neutralize. There is no other pressure force. Okay, this mismatch occurs because this is not atmospheric pressure, it is something else. Okay. Now this is phase number 1. This is phase. Once you identify the pressure force, then it is simple x momentum balance. Right. So it will be Rx plus P1A1 minus P atmosphere A1 is V rho V dot dA. Okay. Now at the phase 1, area normal and velocity in the opposite direction, so it will be minus rho V1 square A1. At phase 2, you will be having V2 issuing out in the opposite, in negative x direction. Okay, V2 is issuing out in the negative x direction because this is positive x, this is positive y. At phase 2, V2 is issuing out in the negative x direction, so it will be minus V2. Okay, and area normal and velocity will be in the same direction. So that in the scalar sign of the scalar product will be 1, will be positive. So rho V2 times A2. Okay, so it turns out to be rho V1 square A1 minus rho V2 square A2.
So this P1 is the gauge pressure.
P1 is the gauge pressure.
So we'll have to consider P atmosphere from this side also. No?
So
So already
it will come out to that. That will do it. No problem. That will be included. This is gauge pressure. But whenever you are doing the balance, you should express it in terms of absolute pressure. Whenever you are doing the balance, you will be taking it absolute pressure. So what is there? It will be minus, if you take it on the right hand side, it will be minus P1 gauge. The whole thing will be replaced by minus P1 gauge. But whenever you are doing the balance, that pressure should be absolute pressure. There is a definition of the gauge pressure, P minus P atmosphere. So P1 gauge will be nothing but P1 minus P atmosphere, and that pressure is known. So we take this on the right hand side and combine this term, and it will be replaced by P1G. So Rx will be minus P1G A1 minus rho V1 square A1 plus V2 square A2. Okay. Now if you put all the numbers, then it turns out to be 371 Newton. Okay. So reaction force on elbow is 371 Newton towards right. Okay. Do you have any of you is having a class after this? Then we will stop here, and we will be doing some problems on moving frame of reference in the next class. Okay. Thank you.